Thermal radiation is all around us, and here on Earth, at general temperatures that we experience, this is in the form primarily of infrared radiation. This can be picked up with infrared cameras. But as you increase the temperature, the wavelengths get shorter. So if you get something really hot, first you'll start to get red light, and then you'll go up through the color spectrum, eventually getting all visible light, which you get white light from. This is shown in an incandescent light bulb where the filament, the tungsten filament, gets so hot that it starts producing visible light, but it still also produces infrared light. In fact, most of the energy from an incandescent light bulb is invisible infrared light. Now, the sun also produces thermal radiation, but again, as you increase the temperature, the wavelengths get shorter. So the sun will actually produce ultraviolet light, even X-rays and gamma rays. But another thing too is that as the temperature goes up, the wavelengths get more broadly distributed. So, for example, with something colder, say the heat of a body, you'll have infrared radiation, but those wavelengths will be primarily focused around a certain wavelength. But as you get hotter, you get more broadly distributed. So something hotter doesn't just produce shorter wavelengths. It produces shorter wavelengths, but it still also produces the longer wavelengths, and it produces wavelengths all across the spectrum. Now, something interesting about the sun in particular is that the photons coming from the sun that we see are due to thermal radiation. They're not actually due directly to the fusion going on in the sun, because what happens when you have fusion, you have hydrogen atoms coming together, forming helium, and that releases energy in the form of gamma rays. But those gamma rays are primarily not what we see. The gamma rays simply heat the plasma of the sun enough so that the heated plasma produces thermal radiation that we see. Now, another thing with thermal radiation too is that not all materials emit the same way. So if you wanted to quantify something and you have a surface, you can measure how much energy is actually coming off the surface by multiplying a constant by another constant dependent on what the material is made out of, called the emissivity, and this emissivity is between 0 and 1. And then you can multiply that by the absolute temperature to the fourth power, which means that if the emissivity stays the same, say you have an emissivity of 1, and that in this case would be considered a black body that has an emissivity of 1. If you take the temperature, say it's 300 Kelvin, which is like 27 degrees Celsius, so like 80 something degrees Fahrenheit. If you have 300 Kelvin and you increase it to 600 Kelvin, which is really hot, you've doubled the absolute temperature, so that what happens is now, instead of putting out twice as much or 4 times as much energy, it's putting out 16 times as much energy. So the temperature follows with the fourth power of the absolute temperature. And down at temperatures that are typical on Earth, we don't actually consider thermal radiation so much. For example, if you're designing a house and you want to know how much energy is going to go through the walls and escape, depending on how thick the insulation is, you actually don't even really care about thermal radiation. You primarily care about convection and conduction. But thermal radiation is important if you're talking about something like planet Earth, which is suspended in a vacuum. Since it's not in direct contact with the vacuum, you can't have conduction or convection through a vacuum. We care about the thermal radiation leaving the Earth. And what greenhouse gases do is, say you have the Earth's surface and you have all this air above the Earth's surface, greenhouse gases will absorb more of the infrared light that is coming from the surface. So say you have a surface with no atmosphere. Let's say we have a planet with no atmosphere, and the surface gets, say it's 40 degrees Celsius, like 100 or so degrees Fahrenheit, the radiation will go out into space. But if you have greenhouse gases like water vapor, methane, carbon dioxide, some of that will get absorbed into the atmosphere, and it can circulate back to the surface even, but not all of it gets absorbed, and it basically slows down how fast the heat can escape. Another interesting thing about thermal radiation is we know about like nuclear radiation. We can have beta particles, which are free electrons, and alpha particles, which are helium atoms stripped of their electrons. And then we have gamma rays, which are shortwave electromagnetic radiation. And then we also have neutron radiation, which is bare neutrons. But then when you have like a nuclear blast, it emits broad spectrum EM radiation, including visible light and infrared thermal radiation. So one of the big damaging aspects of the explosion to start with, before you have the fallout, is actually the burns, because if you're in the line of sight of the weapon, and you could even see this, pictures of people in Hiroshima who had like designs on their shirt, like some of it was darker and some of it was lighter. The thermal radiation blast, like, it's so powerful that it burns everything. And what happened was, the people with the lighter colors, it reflected more of the thermal radiation, and the darker colors absorbed more of it and got hotter. So they actually had burns on their skin that matched the designs on their they had burns on their skin that matched the designs on their shirt. So that's one thing people, I think, don't think about, is how the heat can actually be one of the worst aspects of a weapon like that. Another thing too is how the emissivity, as I mentioned, can kind of be one of the factors in how much radiation is coming off an object. For example, say I have two objects at the exact same temperature. One of them has an emissivity of 0.9 and another one has a emissivity of 0.45. If they're at the same temperature, the one with the emissivity of 0.45 is going to be putting out half as much thermal radiation as the one that is 0.9. This can be used to help insulate things, like you have these reflective polished metal surfaces which tend to have very low emissivities to insulate. And another thing too is they actually reflect thermal radiation and visible light even too, so that they don't get the heat from the outside and they don't let the heat out from the inside. Something interesting about ice too is that ice has, you can have different absorptions and different emissivities with different wavelengths. So ice, for example, has a high emissivity in terms of infrared light. It lets out the heat easily, but it reflects visible light. So the visible light coming in doesn't heat it up, but then it's allowed to expend heat through infrared light, so it's able to keep things really cold. This is a reason why having ice caps on the Earth keeps those places cold. And another aspect with emissivity too is that the emissivity can change, the overall emissivity can change with temperature, because again, you have a distribution of wavelengths that come from thermal radiation, and the emissivity at those wavelengths can actually be different though. So things can kind of get pretty complicated. But thermal radiation is not something that is typically of concern when dealing with typical temperatures. It's mainly conduction and convection that we worry about, which is why this subject is not explored in depth, even in physics or general level physics, or even in a heat transfer course you might take in at the college level. It's much less emphasized because primarily we're dealing with conduction and convection as being the primary drivers of heat transfer with most of the applications we're dealing with. But I think it's an interesting topic, and that's why I brought it up. But that's it.